think about the answer to that. Thank you. So about as I was entering grad school, the copper oxide superconductors were discovered about a few months before. And I started there and then on C60. So C60 was discovered right around that time as well. And I did work on both. And then transitioned more into nanotubes, so not so far from nanothreads. I participated in the discovery of boron nitride nanotubes. Although I was a theorist, I didn't like I was actually in the lab doing it, but I helped interpret the data and figure out what they had made and what it meant. Came to Penn State, I did more stuff on nanotubes. I sort of branched out in a million other directions. Helped develop the idea of artificial frustrated magnets, which are little domains of metal bar magnets and patterns that some of those ideas of frustration actually apply to nanothreads as well, at least some of the general thoughts there. And just a whole bunch of other things along the way. John Badding and I were collaborators on a project, which was nothing to do with nanothreads. It was about hydrogen storage, in theory involving high pressures maybe, but it was kind of a funky idea that frankly probably wasn't going to pan out. And John brought this X-ray diffraction data from a different project to the meeting and said that, we had compressed benzene, Tom, my student compressed benzene. He gave him credit, said Tom wanted to do it. It wasn't my idea. Data came out. It turned out the machine they used could only compress slowly. It was just a limitation of the pressure control. And what they got out was X-ray scattering that showed a very sharp peak, one very sharp peak, and then some other somewhat less sharp features. John immediately knew it was significant. He's like, typically amorphous stuff comes out when you try something like this. And this is some kind of ordered carbon. We don't know what it is. Do you want to, he sort of showed me the data, said, what do you think? And he had somebody, Tom or John or both, or maybe somebody else had indexed to a hexagonal lattice, 2D hexagonal lattice. Which was a very tentative indexing because there was just one strong peak, which is not good enough to index to anything, right? And then a few sort of weaker features. But it was consistent with that. And that led to the thought of graphene, because it's got the same composition as benzene, 1 carbon, 1 hydrogen. And it's 2-dimensional and it's hexagonal, right? So everything sounds good, except the lattice constant is way off. The lattice constant doesn't even come close to being right. So I very clearly remember the thought process in my head, right there at that meeting, thinking, okay, I see why you thought about graphene, of course, and I see the idea that you want to polymerize this 3-dimensional molecular crystal in some reduced dimensionality, right? You don't want it polymerizing willy-nilly in every direction, because that's where the amorphous stuff comes from. You have a 2D diffraction pattern that you fit to, which is consistent with the idea that it doesn't polymerize in all 3 directions, right? Sort of, lower dimensional pattern at least. But the idea, and this is where my glimmers of synthetic chemistry knowledge came in useful, that I thought, I'm not sure, I don't see how benzene polymerizes in a 2D sheet, because the hydrogen atoms are in the way. How is it going to do that? It seems difficult. Things are going to have to be just right and go up and down in some nice way. So I thought, maybe instead of polymerizing in 2 dimensions and then sort of stacking things somehow in one, that it polymerized in 1 dimension and then you packed them in 2. And that immediately was attractive for 2 reasons. One, I could imagine the benzenes reacting more easily that way. And also I knew that 1-dimensional sort of cylindrical objects would pack hexagonally. That was just the thing that they would do with, very robustly. We were sort of in a project using carbon nanostructures for hydrogen storage. So I had a background in carbon nanostructures, and I had several, 11, 12 years before at Penn State, looked at the idea just from geometry that, this is the other piece of organic chemistry that I knew. I knew that there was cyclohexane, and that it was very happy, because I'd been spending many years thinking about, carbon 6-fold rings for nanotubes and fullerenes and graphene, and although graphene came later. And so I thought, if I just say every sp3 carbon can only make 3 bonds to neighboring carbons, and I say the 4th bond is used up somehow, then it makes 6-fold rings with 3-fold vertices, which are the mathematical rules you need to make all of the fullerenes, the nanotubes and the closed shells and everything else. The only difference is the 3 bonds are not coplanar anymore, because there's 3 of 4 tetrahedron. So if you do make a tube out of it, it comes out very small. So in the process of playing around with that, we also accidentally discovered the adamantanes. And not being sufficiently ignorant, we had no idea they were well known. I went to Tom Maluk with them, and I said, Tom, at my student Beiyang, he found these really stable molecules. He said, yeah, but nobody had made the long, skinny, super long and skinny adamantanes, so we were good there. And we came at it completely from the geometrical argument of nanotubes. So we had looked at that system, we had published on it. And so it immediately came to mind, because I knew it had the right composition. And I just sort of roughly speaking, because I didn't have the numbers in front of me, I thought it seemed like it was about the right size. The lattice constant seemed about right. So in that meeting, so basically I was quiet for like 2 minutes. And then I said, John, I have an idea what this might be. We calculated something. We need to go check the lattice constant. I'll get back to you. So we went and checked. And of course, there's many ways of making a thread, which you didn't appreciate at the time, how many there were, but we had at least done a couple of them at that point for different reasons. And they all have about the same size. So the lattice constant matched. So that was one of the more fun discoveries, I have to say. I'm not just saying that because this is the Nanothread Center. That actually is one of the more fun things. Well, it's awesome. It's sort of interesting. I mean, we had no idea this was the way to make them. So it's not like we predicted how to make them. And for a lot of things, predicting that is the hard part. If I think of what I'm most proud of, I'm not sort of most proud of having predicted them, because it was actually kind of obvious that they were a thing that could happen. And theorists can imagine a lot of things that could happen, but most of them don't happen in real life because it's just too hard to get the atoms to do that. The most cool and fun about it was that I figured out that's what they were from the X-ray data, or at least that could be what they were, right? I mean, that's sort of the thing where I was, sort of confronted with just mystery and structureless information, right? That has it's not like a homework assignment where you're doing, some electrochemistry chapter that week, so the answer is going to involve electrochemistry or something. This is just like, okay, look, here's a peak, right? Here's a couple peaks, and then a blank slate. Seeing that these things were very likely threads, right? 1-dimensional sp3 carbon was cool, but constant concern from there forward for some time that it might just be a one-off. That it's just like, okay, this is just a thing that benzene happens to do because it's got the perfect crystal structure at high pressure to make this happen. and it's not going to happen for anything else, and it's not going to happen in any other circumstance. We just really lucked out in what we did. And in which case, it would still be cool, and you could still say, one-dimensional sp3 carbon, but what would it turn into, right? It would just sort of stay its own very niche little thing. When it worked for purity, was to me almost equally significant, because crystal structure is different, and the molecule is different, and the symmetry is different, and it made the same thing. And at that point, I figured if there are two, there are probably 40 or 50 or an uncountable number of these. But we had to get from 1 to 2, right? And then of course, it went higher than 2. And now we're riding that train. I am an introvert, absolutely. And how obvious that is, I don't know. I was very quiet as a kid. I did not like public speaking at all. And would just think about the bad things that could happen. As far as doing science, being especially, maybe not especially, but certainly for being a theorist, you do a lot of what you're doing is thinking, trying to fit clues together. So there's something internal about that process, at least sort of the self-awareness of how those mental tools work and how to make them work better. And, and nature doesn't care about any of that, right? It's going to do what it does. Being sort of trying to train yourself to notice things, even if they may cause a little bit of, sort of psychic discomfort at some level. But if you sort of decide, well, it would be less comfortable to not know that it was there, then you look. So I'm from a big family. So I'm 7th of 8 children, and both of my parents, PhD chemists. My brothers and sisters, 7 of the 8 are in science or science adjacent fields. So the idea of doing something related to science was in the air all the way through, not necessarily explicitly. Like, no one ever made an expectation of any kind. My parents were, wouldn't do that really. There's none of this like, you should be a doctor sort of, dynamic that, you hear. There's none of that really. The earliest I had a sense of what I wanted to do that had any specificity to it was probably 7th or 8th grade when I was reading astronomy books. I got my hands on some high school astronomy textbook. And then that sort of turned into a theoretical astrophysicist as an undergrad, or a high energy physicist, which is basically just, the child who doesn't know how to stop asking why, just keeping going and just ending up in theoretical physics, or astronomy, because that's sort of where those question, sequences end a lot of the time. And then some interesting thing happened in graduate school that shifted more to condensed matter / materials / solid state chemistry. Roundabout way, the reason for that is that the person who took over graduate admissions in the Berkeley physics department the year before, or 2 years before maybe, was very good at their job. And they had hired a huge class in the class before our class. So then our class had to be smaller. And in the winnowing process of admitting our class, they ended up admitting a very large fraction of people who wanted to do high energy particle theory. They knew they couldn't all do it. So they sort of took us all there in the first week and said, okay, everybody raise your hands who wants to do high energy particle theory. 2/3 of us raise our hands. And there's just sort of this little message like, you're not all gonna be able to do that. The romanticism, the childlike romanticism of, I'm going to solve the theory of the universe by doing this theoretical, high energy physics. And then you sort of, you get close enough to see people actually working on things and you realize, people don't regularly like solve the mystery of the universe sort of on a weekly, daily basis, like, oh, this afternoon, I solved it, and then the next morning I'll just polish it up. You're more just, beating your head against some problem or working out some niche of this or that or something, right? You're working on some human scale fragment of such a thing. And what you actually do day to day in theory is not so different in high energy as in condensed matter, low energy, stuff, solid state chemistry, solid state physics. It's actually not that different. As a theorist, actually, on the low energy side, you actually have a lot more science to look at because you don't need an $8 billion particle accelerator to do it. So there's, so yeah, that's how I got in condensed matter. And then in condensed matter, I aimed my, part of that introversion is that I tend to, when I see where a field is moving, I tend to go in a different direction. So the, if I see many people going at some problem, two thoughts come to my head. One of them is, okay, I guess they're going to start figuring things out. And do I want to be working on the same problems? And then, sort of in that, maybe sometimes I'll figure it out 3 to 6 months before somebody else does, because it's sort of the thing that everybody's working on. And that was very not attractive, both because it meant your impact, even though you might get credit for it and even get famous for something, if somebody else could have done it 6 months later, it's not really that big a deal. Partly that sense of, if I make a different take on things, then I'm more likely to come up with something that maybe wouldn't have been come up with so soon. Or maybe not even at all at some time scale. And also I'd be worried less about getting scooped by somebody who's working on the same thing. So the idea of being trained as a scientist to sort of think about things the right way, meaning to think about very carefully, what is it fundamentally that we're trying to do here? It's how you make connections between fields. You sort of think, what is the essential element of the scientific, event that I'm trying to understand? What's the really fundamental thing about it? And if you get sort of abstract enough to think about it very fundamentally, then it connects to other ideas. The MRSEC, John was a leader of an effort in the MRSEC related to the high pressure work inside fibers. So as far as actually, interacting on any sort of regular basis beyond just sort of a colleague sort of off in the distance, it was through that, and then through this this hydrogen storage effort, which I think we got to know each other better as working through with nanothreads, because we sort of had a shared discovery there. Asking after the scientific welfare, maybe sort of the coin of phrase, just sort of make sure that she got to get a first author paper on this, our stuff is, what's her publications, he was sort of taking on this role for the student who wasn't in his group, right? But just sort of making sure that she was taken care of, and that was a very John sort of thing. We were both Packard fellows, and we would go to these 5-year sort of reunions that they have, and I would not necessarily say there's a specific memory at those, but just both being able to go to those things was very nice, and to remember each location. And going over to the sort of the second house, like not the regular house, but like the parents' house for things, for dinner and whatnot. And Ellie playing with Kathy. Not just interacting more scientifically, but also, you could sense how important it was to him, and developing the field, and he was taking on a center leadership role, right? And he had been an IRG leader before. This was a different sort of thing. And I, at that point, had those kinds of roles in a few different, mostly in the MRSEC, but in a few other things like the MIP. And I was also trying to give him, advice and observations and suggestions and sort of how to do that, right? Well, what does a management, plan look like, and how do we structure the other sides of the center, and what's a strategic plan and all that stuff. John was very, he was a science guy, right? He wanted to be in the lab. He wanted to be building stuff and measuring stuff. So the sort of administrative sides to science, it's not, they were a area of personal development for him, I would say. I'm not gonna say it don't come naturally to him, because I think they did. But I don't think he was in the place to sort of have complete ownership of them prior to that.
This video was produced by the Center for Nanothread Chemistry. In an effort to promote an inclusive and equitable research environment, postdocs and graduate students received the opportunity to interview a senior scientist in the center to nurture new professional relationships during an informal chat with guided discussion questions. Their discussion was recorded, edited, and posted to share their advice, experience in science, scientific challenges, and more.